Hello everyone, my name is Haidar, and I will present our recent research on Aeolian inputs in the Mayab region of Mexico, particularly during the Maya Megadroughts, the time of the Maya collapse at the 8th century. This work explores how dust and volcanic ash may have acted as an environmental buffers. In the Maya area, more than 83 paleoclimatic records have been developed in the Holocene, most of them in lake sediments and speleothems. 54 paleoclimatic records possess information of the climate during the time of the Maya collapse. Most indicate a different degree of drought scenarios and changes to low anthropogenic impact. Here you can see them in yellow. But around 5 in the central lowlands do not have signals of droughts. These ones are represented here in green, whilst other 5 indicate dry periods but still an important human impact here in white circles. During the last classic to terminal classic period, several Maya centers in the south collapsed, even though they had more surface water. Meanwhile, sites in the north, such as the Puk and Cocha regions, persisted or even thrived despite more intense droughts, but disappeared again when the droughts finished. And of course, there are places like Lamanai where nothing happens. This is the case of the Cocha region, where the most important proof of the drought was found in Lake Chancanab, the gypsum layers. The archaeological record shows that the region reached its highest population during the time of the droughts. A similar scenario, for example, here you have the most highest population in the Cocha region during that time. A similar scenario is observed in the Pug region, where the now touristic ancient Uxmal city flourished. As the star Megumbaka Parida shows, here at the right, the region suffered droughts alternate with periods of sea flood. We observed that regions most affected by the drought did not necessarily suffer the greatest societal collapse. Saharan dust, which can be traced using geochemical radius like zirconia and titanium, may have provided critical nutrients to these environments, influencing vegetation, productivity, and soil fertility during stressful periods. In the last 50 years, we have seen that the Saharan dust provide nutrients to the Amazon rainforest. And it has been found in the soils of the Mayab, of the Yucatan Peninsula. The key question is to know if the Saharan dust was present during periods of climate stress, particularly during the Mayan collapse, and if it can be quantifiable. In a similar way, signals releases to volcanic activity has been also found in the soils. This volcanic ash may have also contributed with nutrients in some stressing climate times. Our study focused in the Mujir region on Lake Cana. Here compared with other nearby lakes like Esmeralda and Lake Chancanab. This allows to assess geochemical signatures across space and time to differentiate between dust, volcanic ash, and local inputs. We collected 2 sediment cores, which was studied using, of course, the lake. We did water isotopic signature of the lake. We studied the core, making radiocarbon analysis for dating, XRD for the mineralogy, magnetic susceptibility, XRF, total in and organic carbon. Lake Cana resulted to be the most isolated in the region. However, its signature can change dramatically from winter, here represented, to summer, these are the squares, as the other lakes also behave. Using the Copra algorithm, we developed a robust edge model based on titanium as a proxy. And it was very similar to the Bayesian model developed by Bacon. Importantly, calcium was found to behave independently from titanium. Our lake sediment have layers associated with Saharan dust, when the zirconium titanium per 1000 ratio is over 40. This is represented here by the yellow circles. And with volcanoes and weathering, when is under 40, here represented by the red circles. We can see that the presence of Sahara dust do not maintain a relationship with the runoff in the right plot. Sorry, left plot. We used the aluminium strontium as a runoff proxy and standardized radios such as aluminium strontium, titanium strontium, and strontium calcium to reconstruct effective meteoric rainfall. The temporal alignment of high values in Aeolian proxies with climate in dry phases supports the hypothesis of more Saharan dust in dry times. Here you can see again where is the distribution of the red plots associated with volcanic or weathering, whilst the yellow circles are associated with Saharan dust fluxes. Here you can see also the effective rainfall reconstructed from Cana is quite similar from the effective rainfall that is shown by the proxy of the oxygen isotopes in Lake Chankanaf on the shells of the Pyrophorus coronatus. In this plot, we successfully distinguish the Aeolian signal of Saharan dust from volcanic activity. Lead appears to be a valuable proxy for the intensity of Saharan dust input, as this element is commonly transported with it. However, lead also occurs in layers associated with volcanic eruptions, particularly those that are regional, nervy, and well dated. Here you can see that we have the eruptions of volcanoes, these big bars and their uncertainties. We observe that these volcanic events correspond to the Semian layers with zirconium titanium values below 40, which helps differentiate the lead source. In Saharan dust layers, lead is typically accompanied by elevated levels of silicon and iron, whereas in volcanic ash or weathering-related layers, lead is more commonly associated with sulfur. For example, here in the PCA. Thus, we identify distinctive geochemical fingerprints. Sahara dust is characterized by lead, silicon, and iron, while volcanic inputs are defined by lead, sulfur, and calcium. This distinction allows us to isolate long-range Aeolian inputs from more local or regional volcanic contributions. We were able also to reconstruct the Human Impact Index, which was calculated in two ways. The one used in PCA is a more reliable and this pattern is very similar to the pattern of the Human Index reconstructed in the Lake San Lorenzo near from the settlement of Chincultic in the highlands in the Maya highlands. Davidson suggests Lake Kaname had been disturbed by anthropogenic pressures during the time of the collapse, much more or less, reinforcing its value as a natural archive, which is a little different scenario from the observed in the Cucho region. Remember, we are in the Muyo region, which is a little more to the south, so it's nearest to the Maya highlands. It has been observed that during the period Associated with the Maya collapse, Saharan dust was present during both the early and late phases of the drought. Notably, the highest influx of Saharan dust occurred during the final phases. In contrast, during the middle phase of the drought period, Saharan dust is largely absent and instead replaced by a geochemical signal indicative of volcanic ash, likely associated with the Popocatépetl eruption. This alternating input of Saharan dust and volcanic ash may have provided a continuous supply of nutrients to the soils of the Quechua region, potentially contributing to the region's resilience and relatively independence from the environmental stress of the drought. In essence, this combination may have supported the survival of local populations. Future research should aim to confirm the specific source of these inputs, both Saharan and volcanic, through lead isotope analysis and tephrochronology. We gratefully acknowledge the GAPA UNAM and our collaborators and students who supported this research logistically and analytically. Thank you very much for your attention. We hope this work has reframed how we consider the role of atmospheric inputs in societal resilience to climate stress and how important is the study of lake sediments. And I only have to say, as the ancient Maya, John Butik,